Hello, my friends. This is Dr. Mohamed Nezami again with another lecture. And this time we're going to turn into a new series that is targeting the design and analysis and modeling of the flat panel antenna feed networks. Okay. I'm basically an RF and microwave circuits consultant. So I work independent. If you have any design work that you would like to offload from your organization, my rate is very cheap, very flexible. I could be contacted at this number. I operate of Jordan, Jerash City. You can reach me at this number or this email, and I work with your engineers from specs, from concepts to specs to system modeling to circuit modeling and design and fab files. So basically from ideas to fab files, I work with you and even take you further into the bench testing as well. I specialize in any of DC to 35 gigahertz receivers, transmitters, any type of work in that area. My rate is fixed, $25 an hour, and I give you up ahead how many hours it takes for any design. And so I work with you, and that's it. So today's topic is flat panel antenna array feed networks, part one. Okay, we're going to have several parts on this because I can't cover the whole thing. And the reason I started this, what started this series is I have a graduate student that asked me for assistance, and she was doing some work on that regarding passive antenna feed systems. And I figured, well, this is interesting. This is an area that not a lot of people have talked about. There's a lot of publications on it, but yet, so I said, might as well start a video series on this. There'll be several videos on the not design of the antennas, but design of the feed networks, the network that takes the signal from the transmitters and distribute it to the antenna elements in the array. That's a hefty amount of work. It's very important stage of any radio design, and it's even, I think, if you really examine it, it turns out it's probably more complicated than the antenna array itself. Because the antenna aperture engineers, design engineers, what they do is they assume here is the vector of weights or values of amplitude, distributed values, tapered or uniform on the elements, and they just cite the elements with that, and then they work with that. They don't deal with anything that has to do with the stack layer of that is designed to where one would build the network that distributes the signal from the transmitter power amplifier all the way to all these elements, and then vice versa on the other side, collect the signal from all these receive antenna elements back to a receiver or receivers. So anyway, antenna array, I'm not going to be trying to be a designing antennas here, but we will detail just a little bit on that. Antenna arrays, they're basically arrays that are either a flat panel. They're, as you can see in these pictures here, there's many of them that are spanning applications from, the most current one, which is the SpaceX internet, to radars and satellite receivers, 5G stuff. Why do we do arrays? We do arrays so that we can collect more signal, obviously. We want more gain from the antenna itself. So what we do is, as you know, the array gain in an array is basically a single gain element plus 10 log of the number of elements. So if you have 1,000 elements, that means you're going to have 30 dB of increased gain on top of a single element. You know, you might have a batch antenna that is a few dB gain. Then obviously you have 1,000 of those, or 1 or 2, 4, it's 2 to the n usually. You're going to get 30 plus whatever single unit element gain is. Now, like I said before, antennas can be have wide applications as well in 5G. So you can see these flat panel antennas for 5G and 6G. They're starting to pop out everywhere, almost on buildings, on telephone poles, on utility poles, and so forth, and on the ceiling sometimes. But they're basically really a fully integrated radio. So they do integrate the beamformers as well as the antenna array and subarray, like you see here. This is the SpaceX internet that you see here. Now this is a rectangular one, but this is the rounded one. Okay, and here's that rounded one showing all the sub components in there. Another example in here. So now the antennas in here, the antenna design is, we're assuming that there's an antenna engineer who does the design, and then there's also, it could be the same guy or other guys or girls that would do the feed network, which is as important, and sometimes even more important than the aperture itself. It's more challenging. I've seen, from my experience from the projects I was put on, the feed network turned out to be a very, very complicated and very challenging one to do. So just an example, let's just take a small 2 types of panels. Here's one, and basically this is 16 element one. The feed network is the signal that basically the signal that comes in here and gets distributed using these T-junction splitters that we're going to detail the design of and the theory behind that in this series. So you can see all of this is basically the traces, these traces that what distributes the signal to all these individual antennas is basically the feed array network. Now, we can have either the feed array network could be symmetrical, where it's, you can see that the splitters are all the same width, meaning they're the same impedance. So assuming that this is 50 ohm, the whole network is 50 ohm except this line in here, and this line in here, of course, that has to be 100 ohm in that case, where 200 ohms in parallel would equate to 50 ohm. Or they could be variable ones, like you can see in here. You can see that clearly they're using here variable impedances on the same T-junction. In here, every T-junction has the same 2 widths on both of these lines, which means that this aperture in here, this antenna array, is actually excited or illuminated using uniform amplitude distribution, meaning the power that gets into, that excites each one of those elements is equal. Okay, or roughly equal. Now, where in this one here, you might see that this is actually using tapered distribution feeds. Well, and we will get into that. We will get into what. So the array feed network can be a uniformly distributing the signal, or it could be tapered or windowed design, where the splitting, the dividers actually following a certain distribution of amplitudes. And we will detail in a minute what's the difference between, why would you excite an array with uniform amplitudes versus when you excite them with a windowed or some kind of polynomial coefficient type feed amplitudes. Here's another example. The antenna array feed network is this, what you see here, what distributes the signal to all of these. And basically, in most of the cases, it's really symmetrical. So you start out with a unit cell that is like this, where the amplitude distribution in here, as you can see here, these impedances are different. So this is tapered excitation or illumination. You can see that you can design this here, and once you design here, all you're going to do is just copy it over and over and over. So you can see that this subarray here, all of these are exactly mirror image of this here. And this here is also mirror image of this. And these two are mirror image of these two. So the thing that makes it easier is actually the fact that it is symmetrical, okay? So that it can reduce the amount of work there. What are these dividers that we use? We use basically what distributes the signal on the antennas are dividers or signal splitters. Now, these are all passive, and they can be various types. They can be as simple as a T-junction like you see in here, okay? So they could be T-junctions, but they could also be Wilkinson dividers. They could be rat race hybrids, or they could be 90-degree hybrids or Butler matrix. All of these follow one thing in common, which is the principle of a quarter wave transmission line. A quarter wave transmission line says this: if you have a load, and you have a quarter wave length line in here, the input impedance of this is basically equal to the characteristic impedance of the line itself divided by the load. Likewise, if you're trying to basically match a load to a source, and you have a quarter wave length transformer in here, or a piece of transmission line that is quarter wave length, its characteristic impedance can be designed according to this equation, which is square root of the input impedance, desired impedance, times the load, okay? And so now this value in here, of course, that's what determines the width of these. As you know, the width of these is proportional to the impedance. And you can see that this is a thin line in here. That means this is a higher impedance than this line in here, okay? And this line in here is a thin line. You can see that this is asymmetrical power splitter, where a little piece of the power is going in this high impedance line, while most of it is going into this low impedance line. And you can see that this is here is basically where we start out with the source. Okay, so all of these, regardless of which one we use to implement the antenna array network feeding, okay, the array feeding network, all of these follows a principle in which we can design it using this principle of quarter wave line length line impedance. Now, here are the basic two types of antenna feed array divider networks that we can use. The first one here is a T-junction. You can see it's a T-junction basically because of the shape of this. It's like the letter T in English. So what we have a 50 ohm line, and we have two 50 ohm lines that are going to these here. And of course, at this point in here, you got 50 parallel with 50, that's 25 ohm. And so therefore, if you insert a quarter wave line in here, its impedance would have to follow this equation here. So it's the square root of the input impedance, the source impedance times the load impedance. And so the load in here is 50 in parallel with 50, which is 25, and the source is 50. So therefore, this line in here is 35.4 ohms. And this turned out to be a very commonly used T-junction splitter for antenna feeds, okay? Now, the Wilkinson divider is a very popular divider, okay? And this divider in here is a little bit different than this because it basically has, as you can, I'm not going to go from basics of Wilkinson divider. I'm going to assume that you have the principles of this, but all it is you got 50 ohm line, and you got two quarter wave lines in here in parallel that splits equally in here, and you've got a 100 ohm line, or twice this impedance in here, whatever happens to be the source impedance. In this case, it's 50, so that resistor is a passive resistor, thick film or thin film. It's 100 ohm. And then you got 250 ohms in here. So this line in here, of course, is always going to be 70.7 if you have 50-50, which is the square root of basically 100, this 100 times 50. This is a quarter wave in here, loaded with 100 ohm, and the source is 50. So therefore, according to this equation here, square root of 50 times 100 is going to give you basically 70.7 ohms. And that's a lot of you, the first introduction to microwave circuits, you take this device here and you probably design it. So what's the difference? Why do we use Wilkinson versus T-junctions, like in this case, it's a lot of times is a real estate and the ease of fabrication. As you can see, the T-junction here doesn't involve having a resistor. That's one thing. Okay, so there is no need for a resistor. And it doesn't use these two type transmission lines. So this one here occupies more real estate than this one here. This one is simple and straightforward, except now, of course, everything has to have advantages and disadvantages. While this is fully matched, if you look in here, it's fully matched, whatever port you're in, and the two ports in here are isolated. So for antennas, if this were, if the signal in here was divided between these two antennas using unequal Wilkinson split divider, whatever the impedance that this antenna sees, it's totally isolated from the other one. So the two terminals here have high isolation, which means this is good. So therefore, the pattern of the antenna and the mutual interference doesn't come into play, doesn't impact your system when you're using this. But of course, can you use this? Obviously, it depends on your situation, whether you can afford having to have this, use an area that accommodates all this, and plus you need to have 100 ohm resistor. Now, if you're doing this on a microstrip line, the 100 ohm resistor is on top. It's a surface mount piece. Well, if this is a strip line, then obviously you need to go Tizer implementation of a thin film resistor, which is basically a small square of Tizer material that is basically has the value of 100 ohm. Now, unlike the Wilkinson divider, this here is basically going to be on the input is fully matched. Yes, it is 50 ohm, but on the output it is not, basically, because you can see that the output in here and in here it is not 50 ohm. So therefore we can the return loss for this, as I will show in a minute, the most you can have is 6 dB on this one here, on these two. Okay, versus, and here it depends on your design, so you can have 15 dB or better on the design of these. So now the Wilkinson divider also, we're going to cover more of the Wilkinson divider in another lecture within this series for antenna feed networks. But just so that we introduce the concept to you, there are various shapes that there are flavors that the Wilkinson divider can come in. It could come in like this, where it's rounded, okay? It could come in like this, which is almost like an ellipse, okay? An oval shape. It could come in like this, where you stretch out the quarter wave lines up vertically, and could have this, so you can have narrower area. Or it could be like this. This is, of course, unequal power splitting. You can see that obvious from here, because we're splitting the power using two quarter wave lines that are unequal. The width of this is higher impedance than this line in here. So the power in here is different than the power in here. This one here is very important when you're doing apertures that are tapered, where the antennas are fed using a profile of a polynomial, whether it's Taylor or Chebyshev or binomial, and we will show in a minute. So once you do that, that means the array, if you were to implement this here using a Wilkinson dividers, so that what that means is that you're going to have each one of these dividers is uniquely different depending on the polynomial coefficients that you're tapering the aperture with, okay? The last ones that we can look at is basically some antennas can be fed, some arrays. They can design the feed array network using 90-degree hybrid like it is here, or a rat race hybrid like here. And the principle of this, like I said again, that all of these devices that we use for the antenna array feed networks to implement these, all of them are based on the principle of quarter wave line impedance, because that's what resonates, that's what transforms the phase and the impedances. So on a 90-degree hybrid, basically all it is a 4-port device. One port is isolated, and 3 ones are used. These 2 And here are outputs, splits, 3 dB splits. And this is an input. And this one here basically is terminated with a resistor to absorb any of the reflections that come back. And the principle of it is really easy. So you come in here, if you put an input in here, the input in here goes through, if it goes this way, it goes through a 90-degree phase shift due to the quarter wave line in here, and it gets in here. While if it goes this way, it's going to go 90-90, so it's 180 in here, 180 in here, and of course this is 90. That means the outputs are always going to be in quadrature, meaning the phase shift between 2 and 3 are always going to be 90-degree. And the same way, if you feed the signal from here to the output is going to act as a summer. So the signal that comes in here goes out in here and goes out in here, and then what goes out in here, likewise, same type. Now, the reflections, you can prove to yourself that if you get a reflection from here or a reflection from this port or this port or this port is always going to come in phase if it's balanced, if this is balanced, and get absorbed in that 50 ohm resistor in here. The principle of this guy here is the same thing too, just like in here. You can trace the signal. So here's an input. If we come in here as an input, we go out here with a 90-degree, and we go out here with a 90-degree. And then what comes out of here is going to be out of phase what comes out on the other side and going to get subtracted in this one. That's why the delta is here. This is called the difference port. So these are way less popular and less used in antenna array feeds, except the Butler matrix, of course. It's based on this. If you have a Butler matrix feed network, it's really going to use this, the 90-degree hybrid. Okay? So now, from now, you should realize that basically what we have basically, if we use a T-junction, and even though it has a disadvantage that it's not fully matched, it is the most popular way of distributing signals to antenna arrays within an aperture. And it can be two types. It can be a uniform dividing the signal so that uniformly it's delivered to every batches. Like in this example, we have 4 antenna elements, an array of 4. Or it could be unequal. This is unequal in here. This is a T-junction that is unequal splitting. And we will show the principle of this, how it works, and the design equations for this, okay? So, okay. Now, this is here is showing the principle. The next session, we will have more on this. But for now, let's just say this. If you have an antenna, it turns out that antennas are like, for instance, like for those of you in signal processing, if you take a pulse and you take the FFT of that pulse. Now, depending on if you have any post processing on that pulse, you can get a different way of representing the energy from that pulse. Now, if you have a pulse that you FFT without any windowing, which we call rectangular windowing, if you don't have anything on it, you get exactly the sine x over x. So you get a main loop, and then let me show you this here, while we're doing. You get a main loop and you get side loop. It's the black one here. The black one is basically is uniformly distributed signal on antennas on an aperture. But I was showing the analogy to pulse shaping in digital communications or in the signal processing. In signal processing, if you have a pulse and you don't shape it, you take the FFT of that, the spectrum of that, is going to show you a sine x over x, and the first side lobe is always going to be 13 dB below the main loop, okay? And that's why in modems and in transmitters and receivers, we do shape the binary pulses so that we can spectrally contain the side lobes, so that because you have an adjacent pulse, and this will accumulate and interfere with adjacent ones. And this is exactly the same analogy in antennas. So if you have an antenna, if you feed it with equal signals to all of the batches or all of the elements, you get a uniform distribution, which is the black in here. So the side lobes are the first side lobe is only 13 dB below the main lobe. And people came in and worked on this and said, wow, we can actually shape the amplitudes to each individual antenna using the feed antenna network, using either a Taylor polynomial, Dolph-Chebyshev, or binomial. And that's what you see in here. So what happens is that you can actually shape the antenna beam so that you can get rid of the side lobes, okay, using these coefficients. And these coefficients are tabulated, well established, and then you can find them in antenna books and on the internet. So basically, you get the number of elements and you get the coefficients, basically, that just dictates what the amplitude, the voltage amplitude on every antenna has to be. And it turns out what all of these polynomials follows a rule of thumb. If it's odd, you get the middle one is 100% 1, and then the other ones are basically gets divided the rest of the energy. Okay, so as you go further and further, if it's even, you get the two middle ones are always equal. So that means it's the T-junction in here for the middle ones is always going to be a symmetrical or uniform T-junction, while the other ones taper off, and you actually get a distribution which dies out to the edges. And that's why a lot of times you see antenna panels where the corners are all removed, because these coefficients, as you go longer and longer, keeps diminishing to the point where the corner ones don't anymore contribute to the antenna pattern. And so mathematically, what this is really, you can go back to the antenna factor function that describes the antenna pattern. These coefficient in here, this number in here, which is usually, if you're doing a beam forming, this here is a complex number which dictates the phase and amplitude of that individual element has, in order to have an overall beam shape that complies. Where if you don't have beam forming, in this case you have fixed, which is, we call it tapered illumination on the antennas. We use these unequal power splitters, either unequal T-junction or unequal Wilkinson divider, and we're going to have equations for these so that we can, depending on the power ratio between these two outputs, we can find out what this width has to be. Okay, and likewise for the Wilkinson as well. We have the equations for those, and they will have one session on this. Okay, so the taper illumination for antennas, basically we can go uniform element feed, which means we don't do any reduction. The ANs are all ones, so every antenna is basically has the same amplitude, and that's what you have, for instance, with these patches here. That's what you have in here. You can see here that the signal here gets split, and it's equally distributed to all of these antennas. While in other ones, like this one here, for instance, you can see that there is a pattern where there are some lines on the T-junction narrower than the other ones. And so you can see that there is a tapered distribution in here because the amplitudes are not equal. Okay? So now, so basically we showed that. So why do you do this? Why do you taper the values? Well, we taper the values, first of all, to reduce interference. So if you have an antenna that points this way, you definitely don't want side lobes that are only 16 dB below the main power. That's a lot of power to radiate adjacently on both sides, and it's all symmetrical, of course. The other thing, they reduce the batch interactions. So if you have an array, you have an element, that element these side lobes will impact the performance, the impedance, and the loading on the adjacent cells. So that's what we do. Now let's just go through some examples. This is another example that shows how this is an array, which is, let's see, 2, 4, 6, 8. So this is 64. This is 8 by 8, which is 64 element array. This one is non-tapered fed, which means it's uniformly illuminated antenna. So this antenna feed network that starts out here gets over here and gets equally distributed to all of these antennas. The signal level is equal everywhere. So this here is really easy to design, this antenna feed network, because all it is a few splitters that are unique, and then the rest are all basically the same. While if it's tapered meaning that you come in here, and let's say if it was tapered using the Taylor polynomial, oh, this is the Chebyshev, let's say the table, this one here, which is an example that we're going to run and show you. If you have 8 elements, you can see here that we have the middle 2 elements are the amplitude is 1 and 1, and then the distribution of the amplitudes on both sides is symmetrical. So we take half of them here, and we can see this network. So we have a splitter that splits the signal equally first time, and then we start splitting each one of those down to these levels. So what you want to do is you want these ones in here to have these amplitudes. So basically you design these here using this type of T-junction with unequal power division, okay? Of course, this is amplitude, so you have to convert this really to voltages. You have to square it, and it's not very trivial. It's not easy. A lot of people look at this and say, oh, that's an easy thing to do. It's really, it's involving a little bit, and I will make it easy for you to look at, okay? This shows it more clear here. So we've got, this is unequal power splitter, and you can see that's all over the place, while this is equal because these two lines are same impedances, and you can see that it's used everywhere, okay? All right, so this here shows you the principle. You can see these from Bozar book or the internet. There's plenty of comparisons between what is the power split, the T-junction power splitter in comparison to the Wilkinson splitter, which involves using a resistor, of course. You can see that the difference is really summarized in the S matrix, the S parameter matrix for both networks, okay? So you can see that for the Wilkinson, the diagonal parameters, which are the SNM or S1, like this one is S11, S22, S33, you can see they're all zero, so there is no reflections on all 3 parts. While the other ones, it's just minus J, which means it's basically a complex number, indicates you got a 90-degree shift, okay? Now, while the T-junction, as you can see in here, the diagonal components, well, the first one is 0, which is S11 here. All the other ones, though, they're half-half. And you can go to the Bozar book, they derive it in there, or some other on the internet. You can search and you can see the derivation of this. It involves odd and even impedance calculations, but it's pretty simple. But you can see that the return loss in here, if the voltage amplitude is 1/2, then if you square this, it'd be 1/4, and 1/4, the 10 log of that is basically minus 10 log of 4, which is 6 dB, which means these the S22, S33 here on these ports are always going to be minus 6 dB at most, okay? And that's the fact here. And it's funny, a lot of times you get students that start tweaking and optimizing and parameterizing a T-junction, not realize that this is the best you can do with a T-junction. You pay a price for its simplicity. All right, so let's just define the antenna array feed network efficiency. And the efficiency is basically you calculate the entire output powers from the dividers, the final dividers that feed the antennas, and basically divide that with the input power. And you get a ratio, power in versus power out. And that ideally that should be 100% efficiency, but it's not. There's losses from radiation, from ohmic losses, and also reconstructive reflection losses. And you can see, so we define, first of all, is the input power as being the magnitude of the Vn, what goes in, square over 2 times the characteristic impedance of the network, of the input network. And of course, the voltage in here, to do power, we need the RMS voltage. So this RMS voltage is really the peak divided by the square root of 2. And if we do that, we square this here, the 2 falls out to the bottom in here, okay? So you end up with this definition for as an input power. While the output power on all of these output ports in here, if it's equally distributed, uniformly distributed, or uniformly illuminated array, it's basically really the sum of these voltages on every individual output divided by 2 Z naught, okay? And so therefore, this is the output, this is the input, and the output is this. If we take the ratio of that, which is the summation of all the powers that gets delivered to every element versus input power, you can see that this ratio in here, we can cancel these, the 2 0 naught, because it's common to numerator and denominator. And once you do that, if you look at that further, really here, if you could, since everything is divided by the same thing in here, if you spread this out, it turns out that all this is really is just the S parameters, the NM parameters, where N and M are the dimensions. Okay, so you take the S parameter magnitudes, you sum them all from from port 1 to all of the other ports, and that's really your efficiency. Okay, let's start looking deeper on the T-junction networks, and we're going to do that next. So we're going to basically look at the design of those, and I'm going to use ADS because it's pretty simple. You can do the designs like this and end up going here and generate the layout and end up with a layout that represents this. So you can do this. And once you're done with the array, so this is just a single 2 by 1. This is just splitting one signal splitter, but we're going to have more and more. So you can copy this over and over many times and end up building an array. Like for instance, let's see, let's look at this here. Okay, so this is a 16 elements, and all it is really is just basically the cascading of all of these, same one that you started with. You can also have it, let's see, you can have it like this here, where we have it, you know, for this type of antennas, like for this type in here. So this one pretty easy to generate. So you can come in basically and design just a single one in here, and you just copy it over and over. Okay, so it's symmetrical. So you have few calculations, and then you just basically, all you need to do is just basically keep track of, you know, you have this, and so you generate the layout, you have a layout and generate the layout and generate this. Of course, this is ADS, and so you can export this once you're done. If you want to prototype this, or you might prototype the entire one, this might be a 64 elements or whatever, you can just go ahead in here and export it to a Gerber, for instance. Let's see, Gerber, and we want to view it, and there you go. This is your Gerber file here, the artwork for the feed network. So you can take this and send it to the fab house and just basically start testing. Okay, so let's get back and look further on this splitters. And that's basically, now it turns out that the T-junction splitters for antenna feed arrays, there are really few of them, few combination of them, because you're dealing with impedances that are either 250 ohm lines in parallel or 200 ohm lines in parallel. So that means you're dealing with either 25 ohm impedance or 50 ohm impedance, or you're dealing with 50 ohm, of course we said that, or the quarter wave transformer that transforms either 50 to 25, which is a 70 ohm, or in this case here, which is you got 50 with 50 in parallel, that's 25, and 25 times 50, that's this piece here is a quarter wave, it turns out it's 35.35 ohm impedance. Or you could do this way, where you have 50 ohm, and now you go in here, and you have a line which is 70 ohm, okay, that transforms this impedance here to 50 ohm on each side, okay, just like you would do to a Wilkinson. So, and that's what you see in this array in here. So you basically see this is like in here, you see, you go in with, might go in with 50 in here. These are 200 ohm lines on both sides. And then you have transformers, so that, no, these are 70 ohms on these here. And you get back, this is 50 ohm in here. So this transformer in here is used here, okay? And so we go to the antenna in here, the antenna impedance itself has an impedance. So we have a quarter wave here that transforms the antenna to 50 ohm in here. And this is 70 ohm in here. That's 50 ohm in here. This is 70 ohm in here. So you can see that this guy here is used all over in this particular array here. So all you do is you build one, you start basically repeating that, except you might need to extend the length of these lines. That's why the feed array, it's not a trivial. So meaning sometimes you need to basically extend the width and keep track of, extend the length so you can come exactly at the distances of the center to center of these elements, because these elements, center to center, they're most likely going to be either a half wavelength or further, half wavelength up to 0.7, 7/10 of a wavelength. So the spacing in here really determines how you're going to design this. So when you design this, you're giving a set of antennas that are spaced, and you know the locations of these. So therefore, you need to start designing with these transformers and extending half wavelength lines until you build up so that you can equally, you have the signal arriving equal with equal phase shift and delay to every one of those elements. So that's why it's not really a trivial thing. If you do a Wilkinson based antenna array feed, that's a little different. Okay, so basically in there you occupy more space, but it's same principle. So basically, like in this case here, it's equal 1-to-1 power divider. So you get a bunch of those. So you just cascade them everywhere, except you add lines to space the spacing so that you can meet your splitters are pointing right to the middle of the array. Now, in some cases, you actually have a mix of both Wilkinson and T-junction. Like in this case, for instance, here, you can see that the antennas in here, the last dividers on the antennas that feeds the antennas is actually Wilkinson, while the other ones are all T. So you can see this T here. This is unequal power splitting here. This is equal power splitting here. You can see that clearly. And you can see the quarter wave line transformer transformation from this point all the way to get to this point. This is unequal power splitter. The same thing in here. Now you can see that this here, this T-junction in here, is a mirror image. This here is mirror image of this. So meaning this splitter in here is exactly this. And this here is exactly this. This here is exactly that. This is exactly that. This is exactly mirror image of this. And why is that? That's because we have to follow the polynomial distribution of amplitudes that is here. So you can see here that the signal is distributed. You go to a particular length, for instance, let's say that we have 8 elements. The 8 elements, we know that we have equal power on the middle two, while the other ones on both sides, they're mirror image. So this is 0.8 on this side, this is 0.8 on that side. The last one in here is 0.35, and the last one on the other side is 0.35, and so forth. I'm not aware of any automated tool that can do all these automated with the CAD systems that we have, HFSS or Pathwave ADS. I'm not aware of anybody that did any app to do basically smart antenna array feed networks, because it does follow, it has a set of rules. And like, for instance, the first rule, we are giving the antenna array places. We have the location coordinates of the inputs to every one of these elements. And then we have the input. And now in the middle, we have to follow a certain distribution of the signal that is based on a taper polynomial, okay? Now, the T-junction, there's an addition to the T-junction that can improve the discontinuity, and this is well established in the references. So you can see that a lot of times they have this little notch in here, because it turns out that most of the reflections are on this side here. You can see demonstrations of the T-junction on online movies on the distribution. You can see all the reflections in here. So they taper the middle with the triangle, and this triangle in here, they have rules for it. So the rules, this is, I think this is from Beaux-Arts, I'm not sure, but you can use either this or this or this here or this. So you can see this one here, you taper the feed line, while these ones you have a rectangular gap notch. This one you have a triangular notch. Well, this one you have a sort of like a ball type batch, and you get the formulas for all of these. So this is the depth of this is 60% of the width on here, and so forth. You can follow these. So, but my recommendation would be to just design it first without any of these things, and you can do these as a post-processing. The T-junction as well, you can see that we are following exactly the MITRE rule of thumb for the 90-degree. This is done for both the Wilkinson and for the T-junction. And this is a rule of thumb also that shows another rule of thumb where you can actually vary this angle and this distance in here to basically minimize the interaction from the discontinuity. So let's look at this small tutorial on some of the I grabbed these from the open literature, showing how these, so let's start out with just a simple 2x2 antenna network where the antenna port is 50 ohm, basically. You can see that in here, we have used, and these are the transformers, basically, like I said before. We either have this one here, which has two 50 ohm lines in parallel with the quarter wave ohm line that matches the 25 ohm to 50. This one matches the 50 to 100, okay? And this one here is basically 200 ohm lines in parallel, which is 50 ohm, so there is no need for a quarter wave line here to do the matching. Okay, so let's look in here, like this one here, for instance, the first split, we come in from 50, and we split 50 on both sides using this type here. So we got a 35 ohm that takes you from 50 to 250 ohm line in parallel. Now we got 50 in here, we got 50 in there. We can't split equally to them without using this one here. So we get this one and we use it there and we're done. Of course, it's a mirror image, so whatever you do to these two, you're doing on these two. This one here is a little bit different. This one actually uses this one here as well. So we come in 50, and then they use 200 ohm lines, okay? And of course, a 100 ohm line, that's probably the max, the highest impedance that you would want to use on the antenna feed networks, because this line is very thin. So depending on the substrate, it could be as low as 5 mils to do a 100 ohm line. Okay, so that's why we need to, a lot of times we need to get away from these small, and they're fragile too, so you could peel off this so easy. So a lot of times they don't use this, but let's see that this individual here chose to do this. You get this here doing the first split, equal split. Okay, so you got 100 ohm in parallel with 100 ohm, that's 50 ohm, and you got feed 50, so you're done here. You don't need to use transformers. Now the element itself is 50, okay? So what he does here is he uses this same splitter in here, again, to go from, let's see, he uses here 50 with 50, no, 200 ohms, and then he uses from 50 to 100, he uses 70 ohm quarter wave line in here, okay? So this one here is not this, because this one here uses another quarter wave transformer, okay? While the batch in here is 50, now we want to transform it to 100, so we use a suction that is 70.7 ohm transformer. So this quarter wave in here, quarter wave in here, quarter wave in here, and so forth. So you can see that we've utilized this plus this here. All right, so next, let's look at this. This is another example that I grabbed. He started with this first, okay, which uses basically this here. So you got 50 ohms and separated by 70 ohm and then 50 ohm. So they have it here, and since this is 50 on this side, again, now you go from 50 to 250 splits, and you use exactly the same one. So they repeated, this is the same transformer is used here, is used here, is used here also, which simplifies the antenna array feed network because all you have is just a single one. So if you come in and decide to use a little notch or some kind of a tweak in the lengths and the dimensions, you basically update that in the entire design, and that's it, you're done. So to make 16 element array out of this, so all we need to do is come in here, basically, is grab this here and make two of them. And then just utilize one of these to do the splitting between them, okay? And that's what he did in here. Now, to do furthermore, now this is here going 16, 16, 32, that's 64, I guess. Are we? 2, 4, this is 4, this is 16, 16, 32, yeah. It's 64 elements. So you do exactly the same. So this is mirror image in here. This here is exact mirror image of this, which is simple. So, okay. Now, of course, the antenna itself, now there are two ways to approach the antenna. I'm not trying to be an antenna designer over here, but if you're dealing with the batch usually the dimensions of the width and height and the input impedance is well established. So these are the equations, depending on your resonance frequency, where you want the batch to resonate at. The reason I want to deal with this is because this plays out the input impedance of the antenna itself, the element itself, can reduce the complexity of the array, of the feed, the antenna, the passive feed network. Okay, like for instance, in this case, watch this. So we can have antennas like this type here. We can have antennas where the impedance can come in and you're forced to use something to transform the input impedance of the antenna, which is in this case about 200 ohms, back to 50 ohm. While this type of antenna here, we have with these inlets in here that you can vary the gap width and the depth of this slit here and actually make this antenna 50 ohm. If you do that, then you obviously don't need any transformation in between, and that simplifies the antenna feed network. That's why if you have an antenna array feed designer and an antenna aperture designer, you need to have them at least interact at the beginning so that you can reduce the complexity of the feed network. So showing you the linear and the circular polarized, the impedance in here, basically, you need to transform it to the main feed line of the antenna array feeder. So you have control over this, and this is just showing you how simple it is to come up with the dimensions of an array with a single unit cell. Okay, now in this one here, of course, now what you do is you use an additional line in here, is a quarter wave line transformer to transform the impedance from whatever this impedance is to this antenna impedance. And that is basically what you see on a lot of these here, these lines in here. This is 50 ohm in this case. In addition to the 50 ohm in here, you might see an additional quarter wave transformer that transforms from 50 to the antenna, unless you have an antenna like this type here, which is 50 ohm, which is designed to be a 50 ohm input antenna. Okay, so this principle. So now, like we talked about this, we said, look at this, how neat this is. So assuming that you have two elements of this type and this type, and we're trying to choose this here. We have a 50 ohm input, and we have 200 ohm line in parallel. And then we have to get back to get from this 100 ohm to this 200 ohm in here with 90-degree transition. So first of all, we transform the 100 to 50 using quarter wave transformer, which is 70 0.7 ohm. Now, with the 50 ohm up to this point, we have to again use another transformer, which is in this case a quarter wave, which is 196.5 times 50, and it turns out that's around 99, which I was just could say 100 ohm. So I would, if I was a designer, I would just put 100 ohm in here because we are using 100 ohm in here. While in this one here, it's exactly that we started feeding the same thing. Now, the only difference is that when we got to here, we didn't need to transform the impedance of the input impedance of the antenna itself to the feed line because it is 50. You can see that this one here is much simpler than this one here. Now again, here's another example from the literature. We've got this here showing you how this is done. So we go in first 50 to 100 ohm lines. So we're done. This is 50, 50. This is 2 per 100 ohm, that's 50. Now we go again, we're going to split, use the same transformer in here to split on both sides, except now this one, now we need to transform the 100 to a 50 ohm line, and we do that with these quarter wave lines in here. Same thing we do here. So all this is just basically, all you do here is just use an additional transformer to transform the impedance from 100 to 50. Now, likewise, just like we said before, it's exactly the same feed. Now we're feeding this type of antenna where we are controlling the inlet here to do the inlet feed point so that we got 50 ohm. This is 50, so we can use actually this, so it's much less. It reduces the dimensions of this because we don't need to use an additional transformer to transform the antenna element impedance to the feed line point. So now, as you can see that these three T-junctions are very prominent in antenna feed networks for equally uniformly illuminated antennas at the element point, but we do use these and also at the early steps of splitting in the tapered designs, because the first two coefficients in the array, the center two are basically the same, so we always use equal splitter. So we have either this, or this, as you can see. So that's why we're going to design these in ADS next. So we have, to do this, I picked the substrate is FR4 with DK of 4.4, and the height of the substrate is 1.5 millimeter. And I chose 3.5 gigahertz as my operating frequency, and I synthesized 4 lines, 50 ohm, 35.3, and 100 ohm, and 70.7 ohm. I got those, the length of the quarter wave transformer and the width of that line, because I want to synthesize these three here. And that's what I did next, and we're going to look at this. So you can see the first one, we came in here and we can start out with a 50 ohm, add another quarter wave here. We have a T-junction in here, okay? And then we split into 50 ohm on both sides, okay? And then a 50 ohm line, we have a 90-degree bend. And that's what we got this. And you can see the performance is exactly 3.5. And the return loss is basically S11 is good, beautiful. S22 and S33 is minus 6 dB, as you can see. And that is basically what we have here in ADS. Let's just close these. So we start out here, which is, this is the 50 and 35. So we start out, sorry, let me open the schematics. So start out with a substrate that is here, define the substrate parameters, and then I define some variables, which is the width of the 35 ohm, almost 5 millimeters, and define the width of the 50, or the width of 35, the width of 70, the width of 100, and then reconstructed this now. And what I simulate this, and we basically get the performance in here. You can see the marker is at this point here, and you can see that we're at 6 dB return loss on both sides. Now, once I'm done with this, I do the layout of this, of course, just to make sure things are All right, so layout, generate the layout. And yes, okay, this, and that's basically what we have. So you can see that these individual lines have all been transformed using the computer to their corresponding one. Okay, don't save. Okay, so let's go to the second transformer. Okay, so we're gonna go, the second transformer I did is the 50 with 270 ohm line sections. So we got oops. Let's open the schematics for that. This is schematics for that. So we've got the 50 ohm line in here, and I've got two quarter wave 70 ohms on both sides, this one and this one. And then I've got 50 ohm is the other line, additional line to have the 90-degree bend, generate the layout for this. And that's basically what we got here. So you can see that it generated this. And if you simulate this, we can simulate this. The performance is going to be very similar to the other one. So basically, got the split network, so about 0.2 dB insertion loss, and this one got 6 dB return loss on the other ports. And this port's resonance, of course, is pretty high, pretty highly matched. Now the third one is basically is this one, and let's see that one. So we've got that guy there. This guy 50. This is I don't think I did that probably. Let's see. Oh, here it is. Okay, so let's get this one. So we got this one. We go on 50, and then we go out 100 ohm on both sides. Okay, and then we use a quarter wave line to do the transfer to. This is a quarter wave section in here. This is to transform to 50 ohm back. So we generate this, can simulate this, and you get exactly the same performance like we had with the other ones. If we generate the layout, and here's the layout of this. Okay, so these are the 100 ohm lines. Okay. Okay, so we got this done. So let's see what else I generated. So we have this. So we did these three lines. So we did the individual lines. And then I went into this. So basically implemented this and this just to show you what's involved. And that's basically, we do the same thing in here. We're doing these, we do this way. Okay, we just cascade them. Okay, I'll get same performance. And if you could copy this over and over to get 16 elements, like this one in this case, for instance. And you could do 16 elements this is this is 8 elements doing the other way. This is 8 elements that are done for a square type array like this. So as you can see, this is like this type of antenna array feed network. This is the feed network board, and this is the batches, and you can see the feed lines at these points in here. Another example showing you how to do this way. Another example showing basically the same thing. Okay, and we have another example in here. You can see further and further grab from. Now we can do, of course, for circularized signals, we can do sublayers of the feed. The antenna feed network can be fabricated as a strip line layer. Okay, this one on a separate layer, this one separate, this one separate. But it still follows exactly the same thing. So you come in here and you split 100 ohm, 50 ohm, you split again. So all these T-junctions, they're following the same exact rules that I did. Same thing in here, another example in here. And that's it. So for this session, we're going to stop here and introduce the next video topic, which is these here. Now, these are more complicated because we have to design individual power dividers based on the ratio of these powers in here, based on these coefficients. So we can come in, we're going to come in and say, we want 0.96 dB, 0.69 power ratio to 1 to 0.96 between this and this, while between this and the other one is 0.87. And when we end up using this unequal T-junction power splitter or the unequal Wilkinson power divider, and all of these are basically implementing this coefficient in here, which is the Tapered coefficient on the antenna factor shaping function that are implementing these here. Okay, so we will do that next time on the next video. So let's get back to the greeting page. I hope this has this will be of benefit to people in this area. I thank you very much. This is Dr. Mohamed Nezami. Please tune in for the next video that I will do antenna feed networks that are using unequal power dividers. They're not the same all. They're basically variable division ratios based on the tapering function coefficients, whether it's Taylor, Chebyshev, or binomial, so forth. So in this one here, we did cover the uniformly illuminated array antennas, and we, as you can see, the main thing to take away from this is that we, for antenna feed network, are very complicated and very crucial in antenna arrays. Basically, we're dealing with a network that is symmetrical, highly symmetrical, redundant. So we need to design a few cells and then just copy and paste all over. But they involve either Wilkinson power splitters or T-junction dividers, mainly T-junction dividers. I would say almost every antenna aperture that I've looked at, it's using a T-junction divider. The only thing we use Wilkinson dividers with the issue with the resistor, the 100 ohm resistor implementation, whether it's in thin film or thick film at lower frequency thick film. Can't do surface mount resistors at, say, past 8 gigahertz. We have to use Tizer thin film fabrication technology. And so that complicates the feed networks. And that's why people turn to T-junction networks, but we have to design them correct. The simulation modeling is good. So once we do all of these, we can take this to the HFSS. We can take the image of these, these dividers in here. Once we design the entire feed, you could take it from, export it from ADS into HFSS if somebody has already the aperture design, the array implemented in there, because most people do antenna aperture designs in HFSS. Or you could build it manually in HFSS. But at least ADS gives you the quick way of rapidly modeling this and verifying the intended design. This is Mohamed Nezami again. You can reach me at this number. I'm available using the phone apps, WhatsApp, and Telegram. I do consulting. If you have any design work, I would welcome you to reach out to me. I could help you. I have clients in the US, in Europe, in India. So if you have any projects, please let me know. I could offer myself as an outside remote designer for you. And I have very happy clients that I've worked with before that you can reach out to them and get references. And I sign an NDA with you, and you basically send me your concept, and we can work with your engineers to implement. Well, this is Mohamed Nezami. Thank you very much, and happy day or evening, and wherever you are. Thank you very much. Have a great day.